Assalamualaikum students. Students, in today's lecture, we are going to do ionization energies across a period. But before starting ionization energy across a period, first tell me, what is ionization energy? It is the energy needed to remove one electron from each atom of 1 mole gaseous atom, right? The definition of first ionization energy is in course. Definition of second and third, they're not going to ask you. They will just ask you the definition of the first. And then you must know how to write the equations. When you take out the first electron, that is called first ionization, then second ionization, then third ionization. Remove a first electron, second electron, third electron from an atom against its nuclear attraction. Now, if in an atom we are taking out electron, we are getting closer toward the nucleus attraction increase. So this ionization energy is increased successive. When this change in quantum shell, like after 2 or 3 electrons, if the next electron is in the next shell, there will be a big jump in the ionization. Because within the same quantum shell, there is gradual rise. When the quantum shell changes, this sharp rise. Right now, next, after successive ionization energy, we use successive ionization energy to find out the group numbers. Like suppose after 3 electrons, there is sharp rise between third and fourth. So group number is 3. If there's sharp rise after fourth and fifth, between fourth and fifth. So fourth electron in the last shell, group 4, right? This way. Now, what happens down the group? What happens down the group? Down the group size increase, nuclear attraction for the valence electron decrease. So less energy is needed to take out the electron. Ionization energy decrease. Across a period, when the sizes are getting smaller, smaller, across a period, the nuclear attraction more, the ionization energy increase. But that is general trend. We have to study this in particular. Look, in an atom, the ionization energy depends on the nuclear attraction for the valence electron, the size, the nuclear attraction, the shielding. It also depends on the change in the subshell and the spin pair repulsion. Like we have to study the across a period in detail. Right? So I'm going to share the screen, but when I'm sharing the screen, you have to share, like, and subscribe the channel. Okay? आप जल्दी से करो ना. करो. There you go. Yes. Now, look. This is what? After 7 electrons, sharp rise for chlorine. 1, 2, 3, 4, 5, 6, 7. The 8th electron is from the next shell. And down the group, what is happening? Size is getting large, nuclear attraction decrease. So to take out electron, need more energy, less energy, less energy. Across a period, proton increase. But number of shells, is there any change? No. Shielding electron, any change? No. The proton increase, attraction increase, the size is getting small, more energy is needed to take out electron. When we go across a period, there are small decrease. Okay, like this I'm going to explain first. Okay, this is the full explanation. Let me tell you one thing. Like this is for period 3. If you understand this, it will help you a lot. Look, this is very important thing. You know, the main issue with you people, with the students, I'm talking about students, that like sometimes you understand and you are thinking that you are writing the perfect thing, but the Cambridge will not give you marks, even not in the Excel, none of the system. Because if the system is asking you that what is happening in phosphorescent sulfur, are they asking you generalized or particular? Your answer must be particular. So look, in sodium, like I'm writing the ionization energy, the energy of the orbitals, energy of the orbital. This is sodium. In sodium, there are how many proton? 11 proton. 12 proton, 13 proton, 14, the protons increase. This is across third period, proton increase. This is 1:2:2 P6 3s1. 1:2:2 P6 3s2. Now tell me,
This
are
is
the
your
proton
aluminium. I'm going to
increase? Is there any change in the subshell or shielding? No. Look, 1:2:2 P6, 1:2:2 P6. Any difference? No. The proton are more, the attraction is more, the ionization energy increase. But when we come to aluminium, there is proton increase. But now 1:2:2 P6, 3:2, 3p1. Look, the 3p1, don't you think that the 3p1 is far from the nucleus as compared to 3s? Like, is there change in the subshell? If this is getting far, it need more energy or less energy? Less than this. Although the proton is more, but since there is increase in the subshell, like the 3p electron, is this far from the nucleus? It has more shielding electron. Its own energy is more. It needs less energy to be removed. The first change is at this place. Now, look. They all have electron in the p. But proton increase, attraction increase. In this place, the p is coming for the first time. It arrived first time. So there is a change. But now proton increase, the attraction increase. But this should be explained this way. Look. Wait, let me tell you one thing. I hope you understand. I'm going to explain it in proper detail. You know, if I explain it to you this way, listen carefully. This is ionization energy. What is the general trend? The general trend is sodium to magnesium to aluminium to silicon to phosphorus across a period, sulfur, chlorine, and argon. The general trend is increased. Why? Because the size is getting smaller. I have not shown the size across a period. Across a period, you know, the size is getting smaller. Across a period, the general trend is what? Increase. Now, if we look at the configuration, this is what? 1:2, 2:2, 2p6, 3s1, then 3s2, then 3p1. Look, in all these, the electron is removed from the p. The protons are more, but here the p is introduced, so it will decrease. You know what is happening now? It will decrease and it's get a bit smaller than aluminium. Not too much, a little bit, but less. Right? Now it lowers. You know, it lowers. Why? Because its last electron is in p. Its last electron is in p drop. P drop, 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 by same amount. Look, they all exactly drop by the same amount. Drop. Why drops? Because it's coming out of the P. But if you look at the situation, look. This increase, but this lowers. Huh? The proton increase, attraction increase. The proton increase, but this electron is in the P, which is far as compared to 3s, so it drops. So the graph become like this. Aluminium, silicon, phosphorus, sulfur, chlorine, argon. The point is they are increasing still. Why? Because the protons are getting more. Here proton increase, but first time the P is introduced, which is far, so the effect is like more clear, obvious, smaller. But in this, now it's getting lower, but due to proton increase, lower due to P, but like the actual trend was this. It's not just aluminium lower. It's the graph is not this way, that it is lowered and then it's again the same. No, it's not the same. They all lowered. Now, another thing, they all lowered. Now again, this is P1, this is P2, this is P3, and this is what P4. Proton increase, proton increase, proton increase. But the electrons are paired up in one orbital, not all. In one orbital, the electrons are paired up. When they are paired up, they are repelling each other. When they are repelling each other, they need more energy or less energy? Less. 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 They're all repelled. They all have spin pair repulsion. But the first time where the spin pair repulsion across a period is introduced, it's at this point, so it's more clear. So what happens? It lowered. But then they are increasing and lowered. You know what happens? In sulfur, it's paired, it's a bit smaller. You know it's how much? I know the values. It is 1,000. It is 1,000 and it is 1,060, and this is what 1,000. So lowered by how much amount? Just 60. It is lowered. It is lowered by the same amount. It's again lowered by the same amount. But why they are increasing? Because protons are getting more. So you know how we draw the graph across a period. It is like this. Ionization energy. I will show you this. Sodium, magnesium, more proton attraction, more. Aluminium, a bit lowered. Then silicon increase, proton increase, phosphorus increase, proton increase. Then sulfur lowered due to what? Spin pair repulsion. And then chlorine increase, proton increase, and argon increase. Right? So there is decrease. Why there is decrease? Because the electron is in the p subshell, which is far from the nucleus as compared to 3s. Why it is lowered? Like they don't ask that, is this just aluminium lowered or all of these are lowered? It's actually all lowered. Why? Their electrons are in P. And then all lowered. Why? Because they're all having spin pair repulsion. Now, why increase? Attraction increase. Attraction, nuclear attraction. And why lowered? Subshell and spin pair repulsion. Look. In aluminium, first ionization energy of aluminium is less than magnesium. Why? In aluminium, the 3p1 electron is far from the nucleus, more shielded at high energy. The 3p1 is far from the nucleus. It has more shielding. It is at high energy as compared to 3s. Why ionization energy of sulfur is lower in phosphorus? In S, in one orbital of the 3p4, has paired electron. One orbital of the 3p4 has paired electron that repel each other, spin pair repulsion, but in phosphorus, all the 3p3 electrons are single. I've explained this fully here. Look, the first drop is due to electron removed from the p. Look, they all drop. In rest of the element, the nuclear attraction increase, so they are getting large. Second drop is due to what? Spin pair repulsion. Simple version of the same graph. This is what 3s1, then 3s2, then 3p1, this 3p2, 3p3, 3p4. So it's far from the nucleus, there is spin pair repulsion. And then you know what I did for you people? The whole up to, from hydrogen to potash. You know what is happening in this graph? It's very interesting. And hydrogen, it is 1s1 and it is 1s2. There is increase in the nuclear attraction. Look, one electron and one proton. Attraction is less. Two proton, two electron. Attraction is more. And then what happened? Quantum shell changes. These are period 1 element, 1 shell. These are period 2 elements, 2 shells. These are period 3 element, 3 shells. 1 shell, 2 shell. Their atoms are bigger. The ionization energy drops so badly because its electron need very less energy. In lithium, in helium, it's nucleus and 2 electron. It's nucleus, 2 electron, and then 1, so it's far. Now it's 2s1, then it's 2s2, then it's 2p1. What is the difference? Like in beryllium, it's what? 1s2, 2s2, and boron. So 1s2, 2s2, 2p1. So what is the difference? The 2p1 is far from the nucleus as compared to 2s2. Then 2p1, 2p2, 2p3, then what? 2p4? What is the difference? 2p3, they are all single. 2p4 paired. These paired need less energy because they are repelling each other. The paired electron, they repel each other. When they repel each other, they need less energy. So I think I explained it over there. In this case, there is introduction of what? There's introduction of what? The p subshell is getting far, then p1, then p2, then p3, then p4. What is the difference? Spin pair repulsion. They're repelling. If they're repelling, they need less energy. If 2 electrons are repelling and you are providing energy, it will take out easily. Right? So, look. So, spin pair repulsion. There is spin pair repulsion, but there are more proton. And now again, what is happening? Quantum shell is changed. The bigger atom. They have 2 shells. They have how many shells? 3 shells. There's drop because quantum shell is more, size is bigger. Energy removal is easy. No, sorry, electron removal is easy. And now again, 3s1, 3s2, look, 2s1, 2s2, 2p1, 2p1 is far, 3p1 is, like it's the same periodicity. Same repetition. Then 2p3, then what? 3p3, then 3p4. So what you will say? There is spin pair repulsion. One orbital has paired electron. One orbital has paired electron. But if I ask you that agree, there is spin pair repulsion. What is happening here? There is spin pair repulsion, but protons are more. Like when they will ask you that why there is such a big drop because quantum shell increased, size is getting large. Why big drop? Quantum shell increase. Why big drop? Quantum shell increase. The atoms are getting larger. Huh? Next, why there is increase in the ionization? Because of increased nuclear attraction in smaller size. Same. Attraction more smaller size. Attraction more smaller size. More attraction, smaller size. But why there is this decrease? Because this electron is what? Far. 2p1 is far from the nucleus. 3p1 is far from the nucleus. One orbital has paired electron that repel. One orbital has paired electron that repel as compared to the 3p3, which is singly filled. So at the end, if I go to the conclusion, what is the conclusion? There is big rise or drop. It is always due to change in quantum shell. There is big, if I go this way, rise. If I come this way, drop, due to change in quantum shell. Small rise and drops are due to what? Change in subshells and spin pair repulsion. Rest of all increase in ionization energy are due to change in nuclear attraction and small atomic radius. Nuclear attraction more, change or more nuclear attraction and small atomic radius. I hope you understand this topic. And up till next class, next recorded lecture, Allah Hafiz. Don't forget to like, subscribe, and share my channel. One thing that I want to tell you, all the notes and all the topical questions, they are available on my website. So you guys are supposed to do past paper practice from there, and for the notes, go there. And if you have any problem, you can contact me on my WhatsApp number. My number is given. You can join my live classes. My WhatsApp number is given. Okay, see you.